perfect timing because now we start. So, any quick questions on anything from last time? Or any quick homework questions? Alright. Alright, so a few things before we get started. If you're in the 9:30 section, which you are, make sure to clean up desks before and after class. I kind of forgot to mention that after class last time, but make sure you do so. I have Zoom office hours tonight from 6 to 7 p.m. Check email for a Zoom link. And since I know some people have been having issues with accessing the lectures on Brightspace, I have decided to put mine on my webpage for the time being. So you see, scroll down for Brightspace lectures, and then there it is. Okay. So lecture 1 is up there, so I might put lecture 2 up later, depending on when that gets uploaded. So just be aware of that if you want to re-access the lecture. So without further ado, let's go ahead and get on to lesson 2 on finding limits numerically. So here's our little motivation. So if we let f of x equal this function 1 over x minus 2 quantity squared, well, what happens? So if we let x equal 2 right away, what ends up happening? So f of 2 would then give us what? It's going to give us 1 over 0, right? But oh, wait a minute, we can't ever do that, because if we divide by 0, we get an undefined function value. So f of x is undefined, at x equals 2. So nothing much we can say past that, but what happens if we were to, say, consider values of x extremely close to 2, but not equaling 2? That's where limits come into play. So, looking at definition 1 here, one-sided limits are values that f of x approaches from either the left or right of a particular value of x. Okay? So that's sort of the way to express that in sort of plain English. Now let's see how to express it using mathematical notation. So, looking at this expression here, this is the same thing as saying, if we have this positive superscript here, then we have the limit of f of x as x approaches c from the right. So another way of saying that is that we focus on values of x slightly larger than c. Okay? So that's if we have a positive superscript. If we have a negative superscript here, it's the same idea, except instead of approaching from the right, we approach from the left. So same definition, except we replace right with left. Okay? So, in other words, values of x slightly smaller than c. Okay? So definition-wise, that's all we can really say for the moment. So any questions on that? Okay. So let's use this on example 2 here. So it says, use the tables below to deduce the limit as x approaches 1 from the left of f of x and from the right if f of x equals 2x plus 3 and round any values to 4 decimal places. Okay? So basically the idea behind this lesson is we fill in these charts and we basically look at what f of x appears to be approaching here, is what essentially we're doing in this lesson. So let's first start off by filling out this chart here. So if x equals 0.9, then this entry here corresponds to what happens if we just let x equal 0.9 in f of x here. So doing that, and so if we plug in 0.9 for x inside our function here, what numerical value are we going to get?
4.8.
4.8, good. Okay. So then the next entry, in a similar fashion, is going to be f of 0.99. So what would that be?
4.98.
Yeah, 4.98, good. Okay. And then from there you get the idea. So plug in 0.999 to get this entry, which should be 4.998. And then from there you can either plug in 0.9999 into our function, or you can sort of pick up a general pattern here in that you could see that this is also going to end up being 4.9998. Okay? So now that we filled out this table, let's go ahead and sort of analyze it. So if x approaches 1 from the left, then f of x appears to be approaching what value? 5, right? So if that's the case, that will mean that our left-hand limit will also correspond to 5. Okay. So now let's go ahead and do the same thing for the right side limit. Okay? So let's start off with 1.1 here, just for a sake of symmetry. So if x equals 1.1, then f of x will equal what? 5.2, good. And if x equals 1.01, 5.02. Okay, you guys can still see that. And then x equals 1.001. 5.002. Okay. And then you can either plug in this value of x here or pick up a general pattern to get 5.0002. Okay? So in this case, if you approach 1 from the right, then f of x will approach 5. Okay, good. So then in this case, the right side limit will also be 5. Okay? So that's basically all of example 2 there. So any questions on that? All right. So notice that if x approaches 1 from either side, well, f of x appears to be approaching 5 from either direction. So that'll sort of give us a sense of motivation for the two-sided limit that you will see on the next page. So, looking at the next page, we get the following. So, the limit of f of x as x approaches c, denoted as such, there's no positive or negative superscripts here. So this exists if the one-sided limits equal each other or agree, depending on which word you feel like using. So in other words, i.e., this says that the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x, and it has to equal some value L. Okay? Otherwise, if the one-sided limits do not equal or agree with each other, then the limit just simply does not exist, which we will abbreviate as DNE for short. So does not exist. Okay? So in the context of example 2, since the one-sided limits agree with each other with the value of 5, that will mean that the limit as x approaches c is simply just going to be 5 in this situation. Okay? So that's that example. So one thing I want to remark on before we move on is that this definition still holds even if the one-sided limits are not finite. So you can have plus or minus infinity and the definition will still hold all the same. So that's one important remark that you'll need to keep in mind for some of the examples below. Okay? So any questions on that? Okay. So let's get this out of here and move on to example 4. So use the tables below to deduce the limit as x approaches 0 from the left and the right, as well as the two-sided limit, if f of x equals sine of x divided by x, and as before, round to 4 decimal places. So what you notice here is that we have another trigonometric function to deal with. So one thing I want to emphasize here is that unless I explicitly say otherwise, or if the homework, quiz, or exams say otherwise in a specific problem, always use radians. Unless the problem explicitly says otherwise. So if, for instance, you are using a one-line calculator such as a TI-30, if you turn it on, the calculator will automatically default to degrees mode. So if you want to go to radians, just press this DRG button here, and boom, you're in radians. So, just as a quick little aside, so taking that into account, let's go ahead and fill in this chart here. So, if x equals negative 0.1, then f of x will equal what? So raise your hand if you have that value. Go ahead.
0.9983.
Good. 0.9983. And then if x equals negative 0.01, then f of x equals what? Let's give someone else a chance. So for negative 0.01, f of x equals what? Let's be a little bit careful now. So if you just focus on the first 4 decimal places, that's right. But what's the 5th decimal place you'd get? So if you round that to 4 decimal places, that ends up with what? Well, if the 5th decimal is 8, the 5th decimal is 8, you have to round up, right? So that means you end up with what? It's 1, right? So 1.0000 is what you end up with in this case. Okay? And then if you do the same thing for the other 2, well, you'll notice that they also end up with the same values, since you end up getting closer and closer to 0 in that case. So those will get you 1.0000 to indicate that we're using a decimal approximation, but it just happens to be 1.0000 to account for that rounding. Okay? So in that case, we have the limits as x goes to 0 from the left of f of x, should then equal what? Yeah, just 1? Good. Okay? So let's maybe to speed things up a little bit, why don't we do this? So how about, let's say, this row does f of 0.1. This row does f of 0.01. You guys do 0.001. And then I guess you guys can do 0.0001. So go ahead and plug in those values of x and see what you get for the right table.
Point 1 would be 0.998.
4 decimal places.
0.9983.
There we go. 0.9983. Good. What'd you get for a point? Any of you guys in this row got?
1.0000.
Yep, 1.0000. Any of you guys in this row?
1.0000.
Yep, 1.0000. And then
1.0000.
yep, 1.0000. So what you may have noticed is that essentially this table here sort of ends up being sort of the flipped, quote-unquote flipped version of what ends up happening here. And one way you can see that is that if you note that sine of x and x are both odd functions, well then f of x will then be an even function, and here's why. Because if you have sine of negative x divided by x, negative x, then noting that sine is odd, you should end up with negative sine of x over negative x. But then you realize, oh wait a minute, these negatives just cancel each other out, so you're just left with f of x. So in this case, you just end up with the fact that f in this case is an even function, so you can use that nice bit of symmetry to help you get some of the values on the right-hand side once you have one of the tables. Okay? So if that's the case, then that will give you that the right-hand limit is also going to be 1. And as a result, the limit as x goes to 0 of f of x will then equal what? Yep, good old 1. Yep. So that's example 4. So any questions on that? All right. So moving on to example 5. Use the tables below to deduce the limit as x approaches 2 from the left from the right, and the two-sided limits of f of x if f of x equals the function 1 over x minus 2 quantity squared from the motivation at the start of the lesson. And again, round 2 4 decimal places. So again, let's go ahead and do the same thing we did before in that, let's see, let's say you guys compute 1.9, you guys compute f of 1.99, you guys compute f of 1.999, then f of 1.9999. Yeah, 100 million for 1.9999. Yep, 100 million, good. Go ahead.
A million for 1.999.
Good. 1 million. Actually, 0 there, good. Okay.
10,000 for 1.99.
10,000, good. And then last but not least,
100.
100, good, for 1.9. So here's what we notice. So if x is getting closer and closer to 2 from the left, we notice that f of x is getting arbitrarily larger and larger. And if you keep getting closer and closer to 2 from 1.9999 onward, then it'll get even larger and larger. So taking that into account, what should that tell you about the limit as x approaches 2 from the left of f of x? What do you think that would be? It's headed to infinity, right. And that's because, well, f of x gets arbitrarily larger as x approaches 2 from the left. Okay. Okay, now let's go ahead and do the same thing with the next table. So this row does f of 2.1, f of 2.01, f of 2.001, and then you guys do at 2.0001. Go ahead. Yep, 100.
10,000.
10,000.
1 million.
Yep, a million.
100 million.
Yep, 100 million. Good. Yep, okay. So, taking that into account, that should end you up with the fact that the limit as x approaches 2 from the right of f of x is then equal to what? Infinity. And then so, the two-sided limit as a result is going to end up being just infinity, right? Because as we said, even if the one-sided limits are still infinity, as long as they agree with each other, then you're okay. The two-sided limit still exists. Okay. So that basically helps to answer the motivation question at the start of the lesson, in that, well, we know f of 2 itself is undefined, but if we keep getting closer and closer to 2 without actually touching 2, then that just says that f of x just gets closer and closer to infinity. That's all that means. So that's basically the way of working with limits in this context. So even though we may not be able to analyze x equals 2 in this case, we can sort of analyze behavior around x equals 2. So any questions on that? Okay. So, example 6. Okay. So use the tables below to deduce the limit as x approaches 1 from the left and the right, and the two-sided limits of f of x if f of x equals x squared minus 3x minus 4 divided by x squared minus 5x plus 4. And then again round to 4 decimal places as needed. So at first you might think, okay, well, let's just keep doing what we did before and go from that. But you have quadratics on top and bottom, and even though you could just keep doing what we've been doing, these quadratics here could give you a potential room for error here. So in this case, let's see if we can simplify f of x in this context to make computations easier. So simplify first to simplify calculations. Okay. So here's what I mean. So we have a quadratic on the numerator and on the denominator. Okay? So what would happen if we factored the quadratics on top and bottom? So let's start with the top. So if we were to break this up as the product of two factors, what would those two factors be?
X minus 4 and x plus 1.
Repeat that?
X minus 4 and then x plus 1.
Okay, good. And then on the bottom, someone else, we would get what?
X minus 4 and x minus 1.
X minus 4 and then x minus 1. Good. But then here's what we notice. So in this case, for our values of x, we're focusing on values of x particularly close to 1. And more specifically, we're not going anywhere near x equals 4 in this case. So in this case, x is not equal to 4. So in that case, that means we can safely cancel out these two factors here. So we can just focus on f of x as x minus 1 over x plus 1 over x minus 1. So what that means, in the context of our calculations, is that all we really need to do is just let x equal these particular values here in just this expression here. That's all we need to do, which will help greatly simplify computations. Okay? So, again, let's go ahead and do the thing we did before. So, these two rows compute f of 0.9, f of 0.99, f of 0.999, and then f of 0.9999. And raise your hand when you get the value. Go ahead.
-19.
Negative 19, good. For f of 0.9. Sorry. 19. Then what about, anyone got negative, f of 0.99?
-199.
Yep, negative 199. And anyone from this row?
Negative 1,999.
Yep. And then,
-19,999.
yep. So then, in this case, that says, all right, so if we were to take the limit as x goes to 1 from the left of f of x, then that should yield what? Let's give someone else a chance. So in this case, it looks like it's getting arbitrarily large, but as an arbitrarily large negative number.
Negative infinity.
Right, so negative infinity in this context. Okay? So that gives you the left-sided limits. Now let's go ahead and do the one-sided limits. So you guys do 1.0001, 1.001, 1.01, and then 1.1. Okay, good. You got f of 1 is 21. Then let's see if we can give some other people in that row a chance. So let's see. Let's pick on you. What's f of 1.01?
Me?
Yeah.
Wouldn't it be 21.001?
Not
Wait.
quite. So if you just let x equal 1.01, then
Right. Which one are we doing?
let's use this one.
Is it? Okay. So then we'd plug in 1.001 for x, correct?
1.01.
1.01, right. Which would then give you, you need to add 1 to that, right?
Yeah, so you add 1 here and then you subtract 1 here.
Okay.
So essentially you have 2.01 over 0.01 essentially. Which would be 201. Good. Okay. And then someone from this row, raise your hand.
2001.
Yep, 2001. And then, let's see.
20,001.
Yep. Okay. So then in this case, that would tell you that the right side limit of 1 from the right of f of x would then be just positive infinity. But, oh wait a minute, the left side limit is negative infinity. So that would tell you that the two-sided limit would be, what would that be? Yeah, it doesn't exist, right? Because these two limits are not the same. So the most you can say about the two-sided limit is that it just doesn't exist. So any questions on that? Okay, cool. So at this point, this would be the point where I would say try on your own /group work. And since we've got about 15 minutes left, what I'll say is that, if you have a plastic face shield, you can work with a partner or a group of 3 depending on your preference, and then say, work on example 7, and then we'll reconvene in about 10 or so minutes. So if you have a plastic face shield, you can go ahead and talk to someone. Otherwise, you can just work on your own for a bit and see what you get. Give you guys about 1 more minute. Okay, let's go ahead and reconvene. So, let's go ahead and fill in these tables first. So for this left one, let's go ahead and go down the row. So for this entry, we should have what? Yep, 9516. And then for this entry, 9950. Good. And then
0.9995.
yep, 9995.
1.0005.
Yep, 1.0000. Good. And so as a result, that should tell you that the limit as x approaches 0 from the left of f of x should be good old 1. Good. Okay. And then for this table of rows, I'll start with 0.0001.
1.0001.
Yep, 1.0001.
1.005.
0005. There we go. And then 0.01. Someone else? Let's give someone else a chance. Sure, go ahead.
1.0050.
Yep, 1.0050. And then 0.01.
1.0517.
Yep, 17. So then that should tell you that the limit as x goes to 0 from the right of f of x should be 1. Good. And then that tells you that the limit as x approaches 0 from, or just at all, two-sided limit, will then be 1. Good. Almost seeing it, almost at the same time. That was good. So there's that, and then I probably should have went through the hint first, but for those watching in distance learning, so what I meant by simplifying first, so if we have x times e to the x minus x over x squared, so for those of you that saw this already, what would that equal? What does that simplify to?
E to the x minus 1 over x.
Yep, e to the x minus 1 over x, because x is not equal to 0 here, so we can cancel out a factor of x on top and bottom. Okay, so that's all I wanted to say. So any other questions on any of that? All right, so I will see you guys on Friday then, or potentially on Zoom office hours tonight if you guys are having any questions on homework. So. Oh yeah, also please make sure to wipe down your tables before you leave.
Do you want us to schedule an appointment for Zoom office hours, or just join the Zoom
You can just show up with the Zoom link. I mean, if
Okay.
you want to set up an individual appointment with me, you can, but just
Okay.
let me know 24 hours in advance.
Okay, thank you.
End of recording.